Short number 4, black holes. The ideal classical gas is a gas formed by non-interacting classical particles. The classical particles in an ideal gas only have kinetic energy. They do not have potential energy because the particles do not interact with each other. The classical particles in an ideal gas move faster at higher temperatures. The total energy of the ideal gas is the sum of the kinetic energy of all particles forming it. At 0 K, all the particles are at rest, therefore, the total energy of the ideal gas is equal to 0 at 0 K. Fermi gas is a gas formed by non-interacting fermions. This means it is formed by non-interacting quantum particles with spin half, for instance, a gas formed by non-interacting electrons or neutrons. Due to Pauli's exclusion principle, there are only a few fermions with the same kinetic energy in the Fermi gas. For this reason, the total energy of the Fermi gas is not equal to 0 at 0 K. The total kinetic energy of a Fermi gas at 0 K is called the Fermi energy. The Fermi energy of a gas formed by many fermions can be very large. For instance, at the last stages of their existence, white dwarf and neutron stars could be considered Fermi gas stars with a large kinetic energy. If the fermions move slowly, the gas could be considered a non-relativistic Fermi gas. However, if the fermions move very fast, the Fermi gas is a relativistic Fermi gas. The total energy of non-relativistic and relativistic Fermi gases has a different dependence on the volume occupied by the gas. The kinetic energy of a Fermi star tends to expand the star. In contrast, the gravitational attraction between different parts of the star tends to compress the star. The total energy of the star is the sum of its kinetic and potential energies. The gravitational potential energy is negative, and its absolute value increases if the size of the star decreases. In contrast, the Fermi energy of a Fermi gas star is positive kinetic energy, and it also increases if the size of the star decreases. The opposite behavior of the star's kinetic and potential energies determines the possible existence of a size of the star where the total energy of the star is minimum. This would be the stable size of the Fermi gas star. Now comes the interesting part. If the fermions forming the Fermi gas star move slowly, the gas could be considered a non-relativistic Fermi gas. However, if the fermions move very fast, the Fermi gas is a relativistic Fermi gas. The total energy of non-relativistic and relativistic Fermi gases has a different dependence on the volume occupied by the gas. A detailed calculation shows that the kinetic energy of a non-relativist Fermi gas star can always compensate the effect of the gravitational attraction. This means that a non-relativist Fermi gas star can never collapse to a point due to the action of gravity. However, if the mass of the star is larger than the Chandrasekhar's mass, then the kinetic energy of a relativist Fermi gas star fails to compensate for the effect of the gravitational attraction. If the mass of a relativistic Fermi gas star is larger than the Chandrasekhar's mass, the star collapses to a point due to the crunching action of gravity. The star transforms itself into a black hole. Then, the existence of black holes constitutes a cosmological confirmation of Einstein's special relativity theory. Details about this topic can be found in a recently published book titled Relativistic and Non-Relativistic Quantum Mechanics, both at once. This book was published in September 2023 by Springer Nature, in the Undergraduate Lecture Notes in Physics book series. The book was written by Professor Luis Breve de Peralta and his collaborators from the Department of Physics and Astronomy at Texas Tech University, Lubbock, Texas, USA. This book is based on the use of the Poveda-Poirier-Breve de Peralta (PPGP) equations. In addition, the authors use the PPGP equations for illuminating discussions about the following topics: the frontiers between the classical and quantum worlds, how the interplay between quantum mechanics and relativity determines the existence of black holes, the observed asymmetry between matter and antimatter. A Spanish translation of this book is also available in BookBaby.